At this time, I was told that I had been made a brigadier general. I learned later that General LeMay was in a meeting with Secretary McNamara. At one point in time, General LeMay was director of research at the Pentagon level, at the Air Force level, and under him he had a lieutenant colonel by the name of Robert McNamara. So this was a subservient individual to four-star General LeMay. Well, now the roles are reversed all of a sudden, and that's when McNamara asked LeMay, how many general officers do you have running these billion-dollar programs? And the B-70 at the time was a $1.4 billion aircraft program. So I got noticed immediately that I was now running the XB-70. And it was kind of startling because all of a sudden I had to shift gears from being a director of laboratories to a program director, which is entirely different. The B-70 program at the time had been programmed to develop 3 aircraft. The number 3 aircraft would be the bombing navigation version. The first aircraft was pretty well handmade. The second airplane was made much better. And of course, the third airplane would have been perfect with the bomb nav system in it. But it was canceled when it was about 75% completed. In fact, I like to tell the story that characteristically in the Air Force, the bombing navigation system is traditionally late, 1 or 2 years late. The airplane is sitting on the ramp ready for that to be put in, and it's waiting for the delivery. In the case of the B-70, believe it or not, the bombing navigation system was on the dock, ready to be installed, and the airplane it was to be installed in was canceled. The wingtips rotated downward at Mach 3, or any supersonic speed, because it contained the airflow underneath the aircraft instead of dissipating it out to either side. So the airplane was riding on the same thing a canoe does when it's powered. You know, it's up there on a crest. And that's the compression lift aspect of it. The engineers that designed it at North American figured that was what would happen, and they confirmed it in wind tunnel tests. So it's nothing more than containing the airflow underneath at supersonic speeds. The airplane itself was a monster, really, a huge airplane, and it was capable of flying to Mach 3. At that same meeting, when we broke up, General LeMay pulled me to one side and said, "Do you think it's ever going to go to Mach 3? And I said, "Yes, sir, it will. It's going to hit Mach 3. In fact, it went to Mach 3.2. And so actually it fulfilled what the intention was. And I watched the program and progress of the B-70. It was coming along fine. The big problem was fuel leaks. When you consider how huge the fuel tanks were and trying to get them to seal properly from leaking fuel, it was just an impossible program. I happen to know, because I was cleared for the information that was being accumulated by the SR-71, that they had solved their fuel leak problem. And I found out that they had a certain contractor who could do it. Then I passed this information on to the North American people. They were very suspicious of where I got the information and how, and I wasn't able to tell them. But I was able to tell them, go to this contractor and he will solve your problem. Well, it was a 1-year delay in production of that aircraft, believe it or not, because of fuel leaks. We'd put a certain type of material down on in the in wings, and then some clown without canvas boots would walk across it and tear it up. Now you got to go through all the curing, applying, and so forth. That's what delayed the airplane considerably. Our big problem was keeping the surface of the airplane properly established. We had trouble with tires. The tires would come up into the wheel well, and they were eventually exposed to about 300 degrees Fahrenheit and would burst, and so they'd have a problem landing with them. So Goodyear had to design different types of tires for the B-70, including interwoven aluminum threads to keep them from rupturing. So it was a nightmare temperature-wise. I wanted to be on the first flight when it flew, and it would be flying out of Palmdale and then land at Edwards Air Force Base, where it would continue its flight test. The chief engineer, Mr. Swanson, said, okay, we can rig up a seat belt, safety belt, on the water tank that's directly behind the two pilots, and we'll equip you with a parachute in case you have to bail out, because the two pilots will be going out in capsules. So he said, I want to show you one thing, however, before we make that decision. And he took me up into the cockpit, and he asked me in a little door to look back, and I'm looking back at an intake with 3 engines embedded in it, and he said, when you go out, where do you think you're going to go? And I said, well, never mind being on the first flight, forget it. Because that huge, like a big house, would have sucked me in. Obviously, I wouldn't have ever been able to survive the crash. The first flight, all the tires blew out. There were streams of flame from going behind the airplane. All of them blew out because the sensing device locked up all the wheels instead of taking the pressure from the cockpit and braking them gradually, as you now have on automobiles and so forth. They locked the minute they applied pressure, brake pressure to the both sides. The wheels locked, the sensing device malfunctioned, they locked, and they blew them all out. I was on the midpoint where they landed at Edwards. I rushed over before they got. They flew about 30 minutes or so in the air and just tested out general characteristics of the airplane. And I saw that airplane land, a beautiful landing, and all those tires blew out. Well, the XB-70 was a favorite punching bag by Secretary McNamara. For some reason, he was convinced we didn't need the B-70 because of ballistic missiles. They would gradually replace any bomber effort. Secretary of Defense decided he didn't want to put the XB-70 into production. Then he suggested We continued the program until expiration of the funds to contribute technology to a so-called national supersonic transport program. So we did continue with the 2 aircraft, and of course the second aircraft was involved in a mid-air collision, and this was when I was in Japan with 5th Air Force. And it was just one of those tragedies that never should have occurred. And a lot of people were disciplined as a result. A GS-15 civilian, which is as senior as they get at the time, was reprimanded because he permitted a so-called photo flight to be authorized with 5 aircraft involved, the B-70 leading it, all equipped with General Electric engines. And so General Electric wanted to capitalize on this, and unfortunately the NACA pilot, NASA now, in a 104 got in too close to the overflow of the huge wing in the B-70 and was pitched up. His aircraft was long enough to take the tips off of the top of both rudders on the B-70. And I had chased the B-70 on a flight in a B-58, which has a lot more inertia. And I got in very close to the wing. When you're flying formation, you normally try to pick a point that you concentrate on to judge your relative motion. It was huge looking at the B-70 wing, and it was tough really to concentrate on any particular point. So I felt being sucked in to the flow over that wing, but the B-58 was large enough on its own that I got out of it. And I think that's what happened to the 104. It didn't have enough inertia and so forth to get back out once it got sucked in and it pitched.
More than 1/4 century after its maiden flight, the XB-70 stands as one of aviation's greatest achievements. This is the XB-70 Valkyrie, a supersonic heavy bomber that featured design innovations decades ahead of the planes of its time. Yet, this revolutionary aircraft never went into service, because while it was being developed, the strategic picture changed. Designed as a replacement for the Boeing B-52, the XB-70 could travel at 3 times the speed of sound, employing technology that was well ahead of its time. The XB-70 is one of the best aircraft designs that never went into production. A decade later, a similar fate almost befell this plane, the B-1 bomber. Apart from modifications to the engine intake, the B-1B seen here looks very similar to its controversial predecessor, the B-1A heavy bomber. However, because of the evolution of technology, the B-1B in many ways was a very different aircraft. Probably the biggest single step forward in the search for new technology to gain higher speed came with the advent of the jet engine. Although pre-war Germany first utilized jet power, American engineers also tested the concept on experimental aircraft before the war's end, with aircraft like Bell's Aerocomet. The first major development of the post-war year was the record-breaking Bell X-1 rocket-powered experimental aircraft. Dropped from a Second World War bomber on December 9, 1946, in the hands of test pilot Chuck Yeager, The X-1 broke the sound barrier for the first time. Further development produced the X-2, which flew faster and higher than its predecessor. The quest for higher speed put phenomenal stress not only on the aircraft, but also on their pilots. The risk of even a minor malfunction at the speeds now being attempted was enormous. Much of the data gathered by the X-airplane tests was used for military objectives. Faster aircraft would be harder targets to hit. Some of the lessons learned from the X-airplane program were applied to American fighters and bombers. With the Cold War on, stretching the boundaries of speed and distance had become a matter of national security. By the mid-50s, the Strategic Air Command, known as SAC, was deploying its first all-jet long-range heavy bomber, Boeing's B-52 Stratofortesss, a giant plane with 8 jet engines suspended below fully swept wings. The B-52 could fly at speeds of 600 miles an hour with a large payload. But although the B-52 was one of the major successes of post-war aviation, it was not supersonic. The next step in the quest to increase the speed of bomber aircraft came with the B-58 Hustler. This delta wing was developed by Convair to produce a bomber aircraft which could actually fly and sustain at supersonic speeds. But to attain this performance, the plane had to be relatively small and could only be classified as a medium bomber. During the early 1950s, when Soviet-America tensions ran high, SAC wanted a bomber at least as large as the B-52, but faster than the Hustler. This was a very tall order for engineers to meet. Taking a heavy bomber past the sound barrier required a phenomenal power source. Temporarily discarding normal jet power as inadequate, aviation companies looked towards two alternatives. The first was nuclear power, used to successfully propel submarines. Convair converted a conventional B-36, not unlike this one, to carry aloft a fully commissioned nuclear reactor. The crewmen were insulated by lead shielding, and although no attempt at this stage was made to transfer power to propel the aircraft, tests were carried out in earnest. Various designs were put forward for bombers which would at least in part be nuclear-powered. However, the biggest problem here was the ramifications of a nuclear-powered plane crashing in a populated area. Another proposal to boost power would be equipping bombers with external tanks of fast-burning zip fuels, such as boron. Prior to the plane making its final dash to its target, the enormous fuel tanks would be dropped, lightening the aircraft for attack. But an ingenious solution to the problem came forth from North American Aviation. The company had refined the concept of compression lift. Their plan called for mounting 6 enormous jet engines in a tapered shape under the aircraft, thus forcing air away from the center section at high speed. The design also allowed for this air to be trapped by the outer edge of the wing when it was lowered. The compressed air would act to lift the aircraft and help propel it 3 times the speed of sound. The design was given the name XB-70, and SAC approved it for development in December 1957. North American had a long string of successes, including the development of the twin-engine Supersonic Vigilante bomber for the US Navy. This aircraft combines speed and bombing capacity never previously available to carry it. But now, having put forward the compression lift concept for a high-speed bomber, North American's big problem was heat. Wind tunnel tests proved the theory could work, but the great speeds the plane would fly at would produce such heat that all conventional materials would warp. To tackle the problem, North American employed a honeycomb sandwich material made from stainless steel. This offered strength and dissipated heat. After 12 months of testing designs and mock-ups, an order was placed for one XB-70. But the aircraft, now called the Valkyrie P-70 as a high-speed research project and limited production to just 2 aircraft. But at least the concept was still alive, and its proponents hoped it still might ultimately be accepted for military use. By 1963, at least one aircraft was well underway. The first XB-70, serial number 20001, must have been an awe-inspiring sight for those lucky enough to see it. But it was not until May 11th, 1964, when the press and public were given their chance to marvel over North American's sleek white wonder. Brigadier General Fred Ascani, who directed the B-70 System Program Office, described the plane's various features.
Most of the structure in the wings and fuselage is of stainless steel. These are our now famous honeycomb core sandwich panels, and many of the outer skins on these honeycomb panels are as thin as 7/1000ths of an inch. The 2-man crew will sit side by side. The crew station in this position is about 20 feet above the ground. All of the space aft of the crew compartment is taken up by fuel, both in the fuselage and in the wing.
Before the XB-70 was poised at the downwind end of Palmdale's 12,000-foot runway for its first flight, numerous ground tests would have to be performed. Shortly after its debut to the public, the aircraft was again up on jacks, while its electrical and hydraulic support systems were thoroughly tested. All moving surfaces were subject to vigorous testing. All flight controls, including the forward canards, the elevons and rudders, were fail-tested and tested again. Like so much of the XB-70, the landing gear, which had to support the plane's phenomenal weight as well as the added stress of landing and takeoff, was for the time a unique and brilliantly designed feature. The forward twin wheels were conventional, but the support gear was required to rotate as well as fold the four-wheeled bogie mechanism, which was stored in the limited space available. The whole process of extending and retracting the clever but complex gear could be achieved in little over 20 seconds. All of the many complex tests that took place during the weeks before the first takeoff were recorded in a special flight test instrumentation package. A self-contained airborne unit. This device was the first of its kind. It was carried in the aircraft's spawn bay, and remained with the plane for ground taxiing and flight tests. The XB-70 prototype was also subjected to vibration tests that were designed to expose the gigantic fuselage and wing surfaces to the effects of vibration far beyond the point it might encounter in flight. As the aircraft test proceeded, aircrews were introduced to some of the engine's characteristics. Here at the Arnold Engineering Development Center in Tennessee, AYJ-93 engine was set up in a simulation of the Valkyrie. The engine was installed in a test chamber to give the flight crew their first experience with its enormous power. The conditions were artificial but similar to what the crew would experience in flight. Seen here is Al White, North American's chief test pilot, the man chosen to command the XB-70's maiden flight. With him is Air Force Colonel Joe Cotton, the co-pilot for much of the early test program. The backup crew shown here are Van Shepard from North American and Lieutenant Colonel Fitzhugh Fulton. For months, these men were embroiled in the business of learning how to fly the world's most advanced and ambitious aviation project. By early September, most of the exhausting static tests had been completed. Now, the most revealing tests would begin. Tests with the aircraft in motion, then, eventually, tests of the XB-70 in flight. Before the engines were fired up, the complicated in-flight recording systems were primed to record every technical event as it occurred. This view of the Valkyrie gives a clear picture of what was to become known as the six-pack tightly grouped together. This phenomenal powerful combination of 6 jet engines were to propel the Valkyrie to speeds considered impossible only a few years before. Now, hundreds of mechanical functions were checked. They would have to perform perfectly if the Valkyrie project was to succeed. The aircraft was removed from all external power sources. After a series of taxi runs, pilots and technicians were satisfied that the Valkyrie was ready for its maiden flight. On September 21st, 1964, The XB-70A positioned itself at the end of the Palmdale runway for a historic moment with North American Aviation and the United States Air Force. Here, as planned, White and Cotton were in the cockpit. At exactly 8:38, the Valkyrie took to the air for the first time to begin a series of epic-making test flights. Accompanied by a single chase plane, simple routine checks were made as the pilots experienced the ways of the Valkyrie in flight. One of the first tasks was to retract the aircraft's advanced landing gear, but the mechanism failed to respond. With hundreds of millions of dollars of high technology in his hands, White set the landing gear back into its original position. The gear slowly responded to the cockpit control. Clearly, the first tests were to be made wheels down. Nevertheless, an alternative plan was available, and the plane continued on its maiden flight, although one engine was shut down when a warning light flashed. Over 60 minutes of valuable testing was gained by the time the aircraft headed back home to Edwards Air Force Base.
50 feet. 30. 20. 10. 5. And you're on. Music.
On landing, one of the rear brakes locked, setting that landing gear on fire. Sitting 20 feet above the ground, with the aircraft handling impeccably, the crew had to be told to the fire by the chase plane. Two weeks after its first flight, with its landing gear, engine, and brake problems all resolved, the XB was ready for its second trial. On an early autumn morning, pilot Al White rotated Test Air Vehicle Number 1 into flight. This time, there were two chase planes so the landing gear retraction could be viewed from both sides. A second attempt was made to lift the gear in flight. Again, anxious moments passed as the chase plane's crews watched. Now, with the landing gear stowed away, the Valkyrie could begin tests at higher speeds. As the plane climbed to altitude, a warning light flashed in the cockpit, alerting the pilots to a minor failure in one of the hydraulic systems. As a precaution, White lowered the landing gear again and pointed the aircraft towards an alternative destination, Rogers Dry Lake, which proved the security of an 11-mile natural runway. The approach was smooth, the brakes operated effectively, and the Valkyrie made a perfect landing. After the flight, it was learned that a fractured pipe had set off the warning light. But considering the enormous complexity of the aircraft, this and the other problems encountered were hardly unexpected. The pilots reported that the Valkyrie behaved in a predictable and comfortable manner. They were coming to terms with the world's most powerful aircraft. While the first prototype was being tested, construction of the second XB-70 proceeded steadily. The massive tubular fuselage was married to the six-pack. The enormous white fins that would direct the Valkyrie were already in place. Lessons learned from the construction for the first prototype rapidly reduced the manufacturing time of Air Vehicle Number 2. The second aircraft differed from the first in a subtle design change. An extra 5-degree dihedral was added to the wings to improve flight stability. Here, one of the massive wingtips is being fitted. This unique feature was, until recently, the largest single moving surface unit fitted to an aircraft. The presence of these wingtips would enable the unique compression lift principles to propel North American's brainchild into the trisonic stage. Back at Edwards, Air Vehicle Number 1 was rising into the sky again. Now, White Cotton and the engineers had sufficient confidence to push the Valkyrie beyond the speed of sound. On no less than 3 occasions, the plane was taken supersonic, then lowered to subsonic flight. But doing this stressed the aircraft, which was designed to be flexible. As a result, much of the thick white paint that covered the aircraft's surface flaked and peeled away. But all concerned would have agreed that it was a small price to pay to get the XB-70 past the speed of sound. However, for this aircraft to reach Mach 3, it would have to go much faster, and testing continued. October 24th saw the plane's fourth takeoff at approximately 40,000 feet. The folding tips, which had previously never been used, were lowered to the halfway position. This would improve the aircraft's stability and reduce the wing drag effect. At this stage, Cotton applied full afterburners to the six-pack, and the slender white shape of the Valkyrie began its steady increase in speed. On October 14, 1965, during its 25th flight, at an altitude of 70,000 feet, wingtips fully lowered, Air Vehicle No. 1 reached its goal, 3 times the speed of sound. But despite its technical success, and its success at meeting SAC's need for a heavy bomber many times faster than the B-58 Hustler, the Valkyrie was not destined to be adopted in military service. The Air Force, knowing the plane would not be accepted as a bomber, had tried to acquire 150 Valkyries for a reconnaissance role. But the survivability of high-flying planes over enemy airspace was now considered doubtful. Soviet anti-aircraft missiles had managed to down a U-2 spy plane which could fly at heights previously considered safe from any attack. Missiles also competed with high-speed bomber concepts within the US Air Force. The SAC now had intercontinental ballistic missiles to carry their nuclear bombs, weapons that were more economical and unstoppable than airplanes. From the early 1960s on, the ICBM was considered the primary means of delivering nuclear weapons. The ICBM also allows the Navy to play a role in strategic bombing, as its submarines offered platforms that were highly mobile and could not be detected. An enormous advantage that the Air Force bombers would not enjoy until the advent of the B-1B and the B-2. Like the XB-70, the B-1A was designed to replace the B-52 as the Strategic Air Command's high-altitude heavy bomber. However, due to political conflicts and technical problems, the project was cancelled. But the B-1 didn't die. Over the next several years, the US Air Force in Rockwell, the plane's manufacturer, revised the aircraft parameters. Taking full advantage of the aircraft's swing wing potential, Rockwell redesigned the plane for long-range, low-level missions. The plane was outfitted with the latest detection evasion electronics. But the major difference between the B-1A and the B-1B is that simply the later model, although the product of considerable technical innovation and years of additional development, was actually made to be slower than its predecessor. Radar jamming and stealth technology have changed the specifications for strategic bombing aircraft. But this is a relatively new development. For much of the century, the military constantly sought faster and faster planes. The XB-70 faced an uncertain future. Despite the Pentagon's decision not to deploy its supersonic bomber, Air Force testing of the 2 XB-70 prototypes continued. One unique feature of the plane, the crew escape capsule, was a masterpiece of engineering. Should the Valkyrie depressurize, the capsule's clam-like top and bottom shells would automatically roll forward and completely engulf the crew member in an airtight module. From there, the pilot would still have limited control over the aircraft, and, if necessary, the entire capsule could be fired from the plane into the air. These capsules were to play a very important part in the final chapter of the Air Vehicle No. 2. Seen here, with its slightly raised wings, the Air Vehicle No. 2 takes off on a routine test mission on June 8, 1966. Al White was in command, but he had a new co-pilot, Major Carl S. Cross, beside him. Cross was an extremely experienced pilot who had just joined the XB-70 project. At 8:27 in the morning after testing, the Valkyrie joined the formation with 4 chase planes. The event would be recorded by an accompanying Learjet. The exercise was simple enough and shouldn't have presented any problems. On the Valkyrie's inside right was an F-104, flown by test pilot Joe Walker. Walker, who was slated to join the XB-70 program, probably had more supersonic experience than any man alive. He recently completed a flight program on North American's X-15, the fastest plane on Earth. Flying below and slightly behind the Valkyrie's right wing, Walker's F-104 starfighter somehow veered too close to the Valkyrie. This shot, taken from the aircraft on the Valkyrie's left, is reversed to give some indication of what Joe Walker may have seen moments before his starfighter collided with the XB-70's wingtip. Possibly, the vector effect on the giant bomber pulled the little fighter into its massive wingtip. In any event, in the matter of seconds, the F-104 was hit and rolled into an inverted position across the top half of the Valkyrie's massive frame. As it did so, it struck both the XB-70's vertical fins and the left wingtip. Therefore, it fell thousands of feet to its destruction. Then, with a dreadful shudder, the Valkyrie rolled over and started on a steep spin. Al White reached for the ejection mechanism within his capsule and fired out of the stricken aircraft seconds before it struck the desert. His co-pilot was not so lucky and remained in the plane. Probably the G-forces of the descent stopped his ejection. By 9:36, Air Vehicle No. 2 was reduced to a smoldering carcass in the desert. Emergency helicopters rushed to the site, but there was little chance that Major Cross could have survived. However, about 10 miles away, the escape capsule containing Al White was spotted. Al was badly injured, and over the next several days, his life hung in the balance. His capsule had not landed correctly, but mercifully, his pilot seat had broken when it reached the ground, reducing the impact. Over the days that followed, technicians and project officials studied the records for clues, but the story was simple enough. Somehow, the little F-104 fighter had accidentally collided with the XB-70. And on that fateful morning, in one action, America lost 2 brave test pilots and one of the only 2 Valkyries ever to be produced. Al White, the Valkyrie's first pilot, and the man who flew more flights on the XB-70 than anyone else, recovered from the crash, but never flew the XB-70 again. After Air Vehicle Number 2 crashed, the remaining XB-70 continued to be tested over a period of 5 years. It was to log 83 test flights, and the research that it, and it alone, could do would provide valuable information for supersonic transport evaluation and many other projects relating to size, weight, heat, and speed. But in some ways, the Valkyrie had also been a military success. Years later, it was learned that the Soviet Union so feared the potential of the XB-70, but it had tried to develop its own smaller version. The Soviets' fear of the Valkyrie was also demonstrated in another way. For it's now known that the Russians developed at a tremendous expense the high-performance MiG-25 Foxbat. This fighter's sole function was to protect Russia from high-flying supersonic bomber aircraft. Aircraft like the Valkyrie. The paradox was that it seems likely that Russian scientists used North American vigilante bombers as patterns for the Foxbat. The similarities are just so close, both in size and in shape, that it seems certain that the Soviet designers used American research of the early 1950s to protect the Soviet Union from American bombers of the 1960s. Eventually, the one remaining Valkyrie was phased out of test service. Air Vehicle Number 1 landed for the last time at Wright-Patterson Air Force Base, home of the United States Air Force Museum. Piloted by Fitzhugh Fulton and Ted Stumfall, it was still collecting valuable data even on its last flight. Shortly before it was signed over to the museum curator, complete with its logbook and a brief ceremony, one of the pilots is reported to have said, "I would give anything to keep the Valkyrie in the air, except pay for it myself." The Valkyrie program has become expensive. The cost of the project, divided by the number of flights, cost American taxpayers $11 million every time it took to the air. But there can be little doubt that North American aviation engineers had not only achieved a technical wonder, they had produced one of the world's truly magnificent and unique planes.
So there were two XB-70s built only to be used for test, and they were extremely effective. They went 3 times the speed of sound, flew nearly to 80,000 feet, and the test program was very successful. Unfortunately, there was an accident in 1966 that had nothing to do with the test. It was an air-to-air collision. But the test program was extremely successful. And everything about the XB-70 is exotic. Every single thing about the XB-70. It had wingtips that drooped down to take advantage of something called compression lift. And basically the idea is the XB-70 at supersonic speed is creating these shock waves. And engineers figured out a way to harness those shock waves so that the XB-70 actually rides on those shock waves. And it generates additional lift. And the wingtips, which were alone as large as the wings on an aircraft, a smaller aircraft, would droop down and help contain that compression and take advantage of the compression lift. There was a large move in 2002, and the existing galleries were created, the Cold War Gallery, World War II Gallery, Korean War Gallery, and so forth. And the idea was to move all of the aircraft that were research and development, move them together in one place. And unfortunately, that place was on the guarded side of the base. But the idea was that when the next building was built, that then they would all move together as one unit over to the new building, rather than tear apart galleries, pulling R&D airplanes out of this one and that one. They would all come over here together. So to see the conclusion of that plan, the vision that was imagined 15 years ago, to see them come over here together and see the XB-70 move back is really very wonderful. Many of us have been waiting about 15 years for this to happen, so it's exciting. Another part of the XB-70 were its advanced engines. They were test engines. They were not production engines. In fact, there are only about 30 or so J93 engines built. It used a special fuel, JP6. And the thrust of a J93, one of these engines on the XB-70, is equivalent to the thrust on a frontline advanced fighter flying today. We've been very fortunate to be able to see some of these aircraft moving in and see this gallery beginning to form. We're very excited when we'll be able to show the public in 2016, and they'll be able to see the Research and Development Gallery, the Space Gallery, the Presidential Gallery, and the Global Reach Gallery. And the staff here is working feverishly to get to that date, and so the public can finally see these wonderful artifacts on display.
A plane designed to fly faster and higher than any of its rivals. The Boeing 707. This is the story of Kennedy's dream, an aircraft at the cutting edge of technology. In the summer of 1963, President John F. Kennedy announces a major new aerospace program.
I'm announcing today that the United States will commit itself to an important new program in civilian aviation.
He calls for America to build and fly a supersonic airline that will cruise at over 3,000 kilometers per hour. One of John Kennedy's heroes was John Glenn, the first American in space. but Glenn was also the first man to fly America coast to coast at supersonic speed in the year 1957. Ever since that flight, Kennedy had dreamed of building an American supersonic transport. Others had that same dream.
The British began their supersonic aircraft program in 1943, midway through the war. It was a design, obviously, at that stage, which called for an aircraft to be capable of Mach 1.5. That's 1.5 times the speed of sound, or about 1,000 miles an hour.
The British had several projects. Among these were the Miles M-52 and the de Havilland DH-108 Smaller. But Britain was beaten to the prize by Chuck Yeager, flying the American Bell X-1.
To tell you the truth, I was hopping mad, because I realized we could have done it and we'd missed the boat by cancellation. Not with the DH-108, but with the Miles M-52. I was to be the pilot of the Miles M-52, so I'd followed this carefully, and we were 80% ready for the first flight when, without any warning, without any consultation, the aircraft was cancelled.
On October the 14th, 1947, the rocket-powered Bell X-1 became the first aircraft to fly faster than sound.
The British were really upset that the Americans had been first through the sound barrier, because British technology was ahead of the Americans. The British just fluffed it, lacked the guts to do it.
The reason the British gave for cancelling the Miles 52 was lack of knowledge surrounding what happens to an aircraft as it approaches the sound barrier.
When an aircraft approaches the speed of sound, several things happen. The most disturbing of which for the occupants of the aircraft is the aircraft begins to shake and rumble, depending on how rapidly or how slowly you approach the speed of sound. But in aerodynamic terms, a wave builds up, an area of compressibility builds up, a shock wave. And what that does is that causes increased drag and increased heating on the aircraft, such that as you approach the speed of sound, as the shock wave passes over the flying surfaces, what that does, it causes the wings to lose lift both above and below the wing. And that has a downward effect on the aircraft. So the aircraft will start to dive if you don't do anything else about it. You'll first start to notice the problem of approaching the transonic area, approaching the speed of sound from about 0.9, so 9/10 of the speed of sound at sea level. And there you'll begin to experience a buffet as the shock wave begins to build up. And as you approach the speed of sound, the closer you get to the speed of sound, the greater that buffet will be, until that moment when you pop through the other side and that shock wave is then traveling behind the aircraft, you then punch through into an area of far more stable air, an area of almost quietness, if you like.
By the mid-1950s, military aircraft were routinely flying beyond the sound barrier. But they did so only for short periods. Sustained supersonic flight was a much bigger problem than just punching a hole in the sound barrier.
Supersonic flight for passengers is actually very different from supersonic flight in the military context. If you're going to fly passengers at supersonic speed, you have to fly them for a long, long time at high speed, whereas military operations tend to be a quick dash.
Only one country decided to tackle the challenge. Defeated in the race through the sound barrier, the British now embarked on the design and development of a supersonic airliner. It was to signal the start of a race that would transform the world of aviation. On March the 10th, 1956, the British re-entered the supersonic stakes with a vengeance, when the experimental Fairy Delta II captured the world absolute speed record at 1,820 kilometers per hour. The Fairy Delta II introduced a series of revolutionary features. A long, narrow delta, perfect for cruising beyond the sound barrier, and a drooping nose to allow the pilot a better view on takeoff and landing. Inspired by the success of the Fairy Delta, the British established a committee to coordinate the development of a supersonic airliner.
The most interesting aspect of the Fairey Delta II that we see on today's Concorde was the drooping nose. Now, what that is it's simply, as you see on Concorde, a nose that kinks. One of the problems with the Delta winged aircraft, and an aircraft that is designed for going supersonic speeds, is that in order to fly very fast, obviously you need something that is as aerodynamic as possible. The problem is they are very, very difficult to fly at low speeds. So when they come into land, they have a very high angle of attack, and very, very difficult then for the pilots to see what they're doing. So they then put this kink in the nose, if you like, to have this cantilevered nose, such that in takeoff and landing, to give the pilots better visibility, they put this design feature in, which we see today.
In March 1959, the preliminary design work had progressed to a point where the Supersonic Transport Committee was able to report its broad recommendations.
There were two main recommendations. The first was for a small, fairly simple aircraft to carry around 100 passengers and do about Mach 1.2. The second design was for a 150-seater that should have been capable of Mach 1.8, which was considerably bigger and considerably faster.
By 1959, the British thinking had crystallized into two projects. A medium-range supersonic airliner, which had a rather crazy M-shaped wing, very difficult to build. And the other project was the classic, what's now the classic long, thin Delta for a supersonic airliner that could fly across the Atlantic.
Now would emerge a decision that would shape the whole future of the race to build a supersonic airliner.
The design study contract in 1960, the British made it a condition to BAC, who got the contract, that they should seek international collaboration for the building of the supersonic transporter.
The first country BAC approached was the United States. But in 1960, there was little interest shown in the USA for collaboration. So the British turned to France as a potential ally.
Eventually decided to cooperate because the supersonic airliner project was just too big for either of them to do on their own. It was helped by the fact that the two different design teams in France and in England had more or less come to the same conclusion about what the aircraft should look like.
The aircraft was to be a delta-winged design. It was to be called Concorde, a word common to both languages, which means agreement or harmony. But to become credible, Concorde needed customers in the airlines. In June 1963, Concorde received the major airline order that meant it would fly. And the order came not from Europe, but from America's own leading airline, Pan Am.
Such a good customer that they could go in and play one aircraft factory leader against another. And Tripp didn't mind going in threatening and saying, look, if you don't do this, I'm going to get somebody else to do it. And if I have to go to Europe, I'm going to Europe. Tripp was an overpowering figure in the industry at that time.
Pan American Airways began operations on October the 28th, 1927, with the first scheduled international flight by a United States airline. A Fokker tri-motor airplane loaded with mail flew from Key West, Florida, and landed 1 hour and 10 minutes later in Havana, Cuba, a distance of 135 kilometers. Pan Am's 28-year-old founder was the legendary Wham Terry Tripp. It was Tripp's original bright idea that planes carrying mail can just as easily transport people. Putting seats in the back of each plane, he charged $100 to fly to Havana. Tripp was determined that Pan Am would always be the #1 U.S. airline.
In the post-war world, in the 1960s, Pan American Airlines was one of the big names. Most American airlines tended to fly inside America, but Pan Am had built his reputation on flying all around the world. And they did that by always buying the latest and best aircraft.
On October the 26th, 1958, Pan Am became the first U.S. airline to operate a jet passenger plane, a Boeing 707 christened Clipper America. It flew from New York to Paris, halving the normal flight time. One trip was also determined Pan Am would be the first airline to go supersonic.
If you joined Pan Am as a pilot in the late 1950s or 1960s, the first thing they told you was, you hang in there, guys, because you are going to fly supersonic. Pan Am saw that being the first to be with the supersonic airliner as the thing that would brand the company as the place to go.
But the Pan Am decision was to trigger an American response. Within days of the announcement, on June the 5th, 1963, President John F. Kennedy proclaimed his government's intention to support the American aircraft industry in developing and building a supersonic transport that American airlines like Pan Am could fly.
When Kennedy heard that Pan American were going to buy the European Concorde, he was apoplectic. He was furious. And he phones up head of Pan Am, one Tripp, and just gives him a bawling out. And Tripp says, well, the alternative is you give me an American supersonic airliner. So from that moment on, Kennedy decides he is going to get a hold of the American aircraft companies and he's going to make them build a supersonic airliner faster and higher in performance than the European rival.
And so the race began.
The immediate result of Kennedy's intervention in the race to build a supersonic transporter was the appropriation of $100 million worth of funding from Congress, which in 1963 was a serious amount of money.
Concorde now had an American rival. The question then became, who was going to build it? One obvious candidate was Douglas, the major builder of civil airliners, from the fabled DC-3 to the jet DC-8. But Douglas was too strapped for cash to compete. Other candidates were North American, who were already working on a big supersonic bomber, the B-70 Valkyrie, and Lockheed, which had major experience of supersonic craft, such as the secret SR-71 Blackbird. There was also Boeing, the manufacturer of the mighty B-52 bomber, and the well-established 707 airliner series.
Of all the American aircraft companies, paradoxically, Boeing was the one that had the most trouble in getting into the supersonic airline business. Boeing hadn't actually delivered a supersonic aircraft to anybody.
Its founder was William Boeing, the son of a wealthy lumberman. In 1903, Boeing dropped out of Yale University and headed for Washington State to make his fortune in the timber industry. In 1910, William Boeing went to Los Angeles for the first American Air Meet. He tried to get a ride in one of the airplanes, but not one of the dozen pilots participating in the event would oblige. Boeing came back to Seattle, determined to build and fly his own planes.
Bill Boeing was, some people think he was an inventor, but Bill Boeing was an innovator of the highest order. I think he has very few patents, perhaps if any, but he would look at a product and he could see where he could make it better.
On July the 15th, 1916, Boeing incorporated his airplane manufacturing business in Seattle, in an old boatyard. He hired boat builders whose skills in carpentry were ideal for the new aviation industry. The early Boeing company prospered, building seaplanes for the U.S. Navy, then pursuit planes for the Army. But it was World War II that brought Boeing to the peak of success.
The war was starting in Europe, and Wright Field put out an order for bids. At this time, most of the airplanes were two-engine. We were still two-engine. Douglas was doing a two-engine bomber, and another company was doing a two-engine bomber. And Boeing went in to Wright Field and said, would this procurement cover a four-engine bomber? And everybody just went berserk because nobody ever conceived of a four-engine bomber.
This was the XB-15, a 4-engine aircraft with a wingspan of 45 meters.
It was so big, you could tunnel out through the wing, and you could come into the nacelle, and you could make repairs in flight.
A smaller version of this giant would become famous, the B-17 Flying Fortress, that would fill the skies during World War II.
I think they ordered 13 or 14 what they call test airplanes, and that led to the Flying Fortress. I don't remember exactly how many were built, but it was around 13,000. And that airplane then went through the A series, B series, C series, all the way to H, as I recall. I'd say the story of the B-17 was it was such a versatile airplane, was able to keep carrying more bombs, more turrets.
As American men went to war, women built airplanes. Thousands of women took up the slack in the workforce and helped boost production at Boeing from 60 planes per month in 1942 to an astounding 362 planes per month by March 1944. The B-17 was followed in 1942 by the B-29 Stratofortesss. In Wichita, farm hands, housewives, and shopkeepers built B-29s on 10-hour shifts, day and night, during what later became known as the Battle of Kansas.
World War II transformed the fortunes of the Boeing company. Before that, it was a serious manufacturer, but planes were built in small numbers. World War II meant Boeing was producing vast numbers of giant bombers on huge assembly lines.
After World War II came the B-47, America's first jet bomber. And on April 15, 1952, Boeing test pilot Tex Johnston made the first flight with the B-52, which was to dominate the skies for the next 50 years. Then, Boeing took a gamble.
In the 1950s, Boeing was doing quite well in military contracts for the B-47 and the B-52 bombers. But no aircraft company, can afford not to look ahead because it takes a long while to develop aircraft. And so they took a bold decision. They decided, well, let's take some of the profits from the bombers, some of that technology, and see if we could mix that into an aircraft that passengers would want to use, that the airlines would want to buy.
We had all the knowledge of the B-47, the B-52, so it wasn't too big a job in the wind tunnel to develop a low-wing airplane that could be used as a tanker. And we knew they needed a tanker, so there had to be a tanker. And we hoped it could be a passenger airplane, although we weren't really sure that that was the case. So that's why the Dash 80 was born.
The Dash 80 took to the air under the control of Tex Johnston, who had flown the B-52. Johnston was determined to show Boeing had built a great plane. So he barrel-rolled the Dash 80 over the Seafair hydroplane course on Lake Washington on August 2, 1955, a maneuver that only nimble fighter aircraft usually do. Boeing's president, William Allen, was there to witness it.
And Allen turned completely white, looked over at his technical advisor, Wellwood Beale, and he said, "Did we authorize that?" And then just before he could turn around, here he came back again and did it once more.
Boeing's gamble paid off. The Dash 80 became the prototype for the KC-135, the first jet aerial tanker. And that turned into the Model 707, the first in a long line of Boeing commercial jet airliners. Boeing had done something clever with the 707. Using about 1/10 of the fuel, the $5 million 706 could carry as many transatlantic passengers a year as the $30 million Queen Mary ocean liner. Boeing had created a market and killed the passenger liner. In 1958, with the 707 entering service with Pan Am, Boeing set up a small group to concentrate on developing a supersonic passenger aircraft. By 1960, the company was spending over $1 million annually on the project. The design was designated the Boeing Model 733.
Boeing actually started work on supersonic passenger airliners very early on, right at the beginning of the 1950s. But in a kind of research way, is this possible? Where are the engines going? Where is the metallurgy going? But what you begin to see is by the end of the 1950s, they're starting to get quite serious about it. They're beginning to think this can be done.
With Kennedy's call for America to actually build the SST, the Model 733 could become reality at last. Throughout late 1963, the three contenders for the prize of building the American SST, Boeing, Lockheed, and North American, worked in secret on their designs. Could the late American competitor still capture the market? In late 1963, nettle for the first Concorde was already being cut. Would America catch up? There was a recent precedent. The British Comet had been the first jet airliner in service in the 1950s. But a series of fatal crashes revealed serious design flaws that had resulted from the Comet being rushed into airline operation to beat the Americans. As a result, the Boeing 707 came from nowhere to dominate the skies of the 1950s and 1960s.
The Americans came late to the supersonic race. They wanted to leapfrog the Europeans, and so they decided to go faster. The Europeans were going for Mach 2.2, which meant they could build Concorde out of existing materials using existing technology. The Americans decided to go way up to Mach 3 through the so-called heat barrier, which meant that because of the stresses on the plane at those speeds and the heat that would build up on the fuselage, they had to use new materials. So the Americans were going for a technological breakthrough to try and get ahead of the Europeans and bury the competition.
To beat the competition, both at home and in Europe, Boeing proposed a plane that was far bigger than Concorde. It was designated the 2707.
Boeing realized that if they were going to beat the Anglo-French Concorde, they would have to be bigger, better, and faster. So their design was for a faster aircraft and for one that would carry 2.5 times the number of passengers as Concorde. So instead of 120, we're looking at 277 passengers on board.
To help design its new 2707, Boeing built an amazing life-size mock-up. The aircraft was 93 meters long, a third bigger than Concorde. There were 277 seats, 30 first class and 247 tourist. 2.5 times the number of passengers the small Concorde was designed to carry. The seating layout in the 2707 was revolutionary. Till then, seating in planes was 2 cramped seats on either side of a single aisle, which made planes seem very claustrophobic.
Boeing decided that in order to entice people into this new aircraft with these fancy speeds, they'd have to offer a bit of something else. And so they made the fuselage bigger so they could get more seating in. Today we are very used to three sets of seats, 2 aisles. But this was the first time when Boeing was developing the supersonic airliner that they decided to introduce that into an aircraft.
By comparison, the Concorde has a very narrow fuselage and the old-fashioned two-abreast single-aisle layout. The 2707 would be powered by 4 massive turbojets, each capable of generating nearly 3 tons of thrust. At takeoff, the 2707 would weigh over 300 tons.
The Boeing 2707 had 2 other very interesting features. The first was a drooping nose, not unlike we see on Concorde today, to allow the pilots much better visibility in takeoff and landing, and then to be flicked up for that needle-like high-speed flight. The second design feature was also to do with the differences between low speeds for approach and landing and high speeds in supersonic, and that was the swing wing. The wing was able to pivot for those slow speed areas, making it easier and safer to fly when taking off and landing. But then when it was up above the Atlantic or Pacific or wherever it was going to go and approaching its speeds of Mach 2, you could sweep the wings back and get a very similar effect to the Delta.
The wings on the mock-up of the Boeing 2707 could be moved manually from fully aft with a 72-degree sweep to fully extended with a 30-degree sweep.
The Boeing Supersonic airliner was really pushing the boundaries of aviation technology. They were going to go faster, they were going to go faster for longer, which meant new materials, new kinds of engines, new kinds of avionics. It was a risk.
One group who thought that were the Lockheed Company, who were busy with their rival SST, the Lockheed L2000.
The Lockheed design for a supersonic airliner was simple, elegant, beautiful. No complex moving parts like a swing wing. They'd adopted the narrow delta that everyone knew was going to work. It was within the boundaries of what was possible. They were minimizing the risks, and that's why it was a serious competitor.
As the time for submitting final design entries drew closer, Boeing was still plotting to outdo the competition.
As the design process went on, it became obvious that the Boeing entry was going to be terribly complex, terribly expensive. That made the airlines who were going to have to buy and use the thing frightened. So Boeing started adding on more and more passengers in the hope that it could make a profit that would make up for the escalating costs of the aircraft in the first place.
Size does help you a little bit on efficiency, at least it has on the other airplanes, and so obviously you can go overboard and be too fast, but too big. But I think that we felt the Concorde was too small to be a successful system.
It was the last day of 1966 when the final design winner was announced. It was the revolutionary Boeing design.
I think it was a very tough competition. The reason we won the configuration was not necessarily that the airlines liked our configuration any better. My personal opinion is that I think that they felt that they would rather have Boeing build their commercial airplane than the other two manufacturers, because we were in the process of building commercial airplanes at that time and been working with the airlines. And my personal opinion is that we were picked as a company, not as a design.
It was a surprise that Boeing won because they had so little experience in building working supersonic aircraft. I mean, they were famous for the B-52 bomber, which is subsonic. Everyone else, I mean, Convair, Lockheed had built large and fairly successful supersonic aircraft. So this was the new guy on the block suddenly being given the job, and everyone thought, can they do it?
Boeing predicted that if design and construction of prototypes began early in 1967, the first flight could be made in early 1970. The first aircraft could then be ready for airline service in mid-1974. They were talking nonsense. They had no idea of the problems they were about to face.
The main problem in designing the Boeing supersonic airliner can be summed up in one word: the weight. This thing just got fat. It got heavier and heavier. It wasn't going to make money. They had to then strip out weight, and in the end, the biggest weight penalty was going to be the mechanism to make the wings swing.
As we got beyond the preliminary design stage to build it, the weight got too heavy. The empty weight got too heavy. That was the main problem. The weight just got out of hand, and we couldn't meet the weight statement that we'd estimated for the configuration at the start.
The project slammed to a halt for a year as Boeing considered alternatives. In October 1968, Boeing emerged with what was virtually a complete redesign.
There was only one way to solve the weight penalty problem. That was to take the swing wing out.
Boeing's swing wing disappeared mostly because of the extra weight. That huge hinge in there was very, very heavy.
The 2707 was also reduced in size. Seating was reduced to 234 passengers, though that was still bigger than Concorde. And now, a new problem appeared to haunt the project and eventually kill it: the sonic boom.
We knew it existed, but frankly, I didn't think it was that bad. The sonic boom that the airplanes we were talking about was like thunder and lightning, where the thunder hits about 2 miles away. And I guess I just didn't figure it was that bad.
In order to explore the effects of the sonic boom on, for example, urban areas, the American Air Force conducted an experiment in 1964, which is something I don't think we would ever contemplate doing today. And what they wanted to do was see what effect it had on an urban area. So they they flew supersonic bombers over Oklahoma City with sonic booms or waves of shocked air passing all the time. The result was that in a very short period of time, they had around 8,000 very vocal complaints and around 5,000 complaints for claims for damages.
In 1967, immediately after Boeing had been selected to build the 2707, Dr. William Shurtleff, a scientist at Harvard University, organized the Citizens League Against the Sonic Boom.
Well, actually, there were so many technical and economic hurdles that had to be addressed for an airplane like this, not the least of which was the sound. Reaching the sound barrier always created a shock wave over populated areas.
Well, that era was a miserable era for me, because here I was, an engineer trying to do things, and you had these idiots back there making it was a political situation, and he just jumped on it. This guy Shurtleff, I never met him. I don't know what his problem was. I know the British were taken by surprise on it. They were completely amazed at the problems we were getting.
Other scientists hypothesized that the exhaust from SSTs, expelled into the atmosphere at high altitude, would start a self-perpetuating chemical reaction that would ultimately deplete a radiation-absorbing layer of ozone in the stratosphere and bring on an increase in skin cancer.
I think there were other environmental concerns, perhaps not substantiated technically, about the ozone layer, about contamination of the upper atmosphere. There were all sorts of boogeymen shoved into the front of the table having to do with so-called environmental problems.
But public opinion was turning against the SST, and as resistance grew, Congress itself began to express doubts about the plane. In response, President Richard Nixon, shortly after he was elected in 1968, appointed a 12-member committee to report on the project.
Nixon was a firm believer in the SST when he came to power, like Presidents Johnson and Kennedy before him, and he felt that the SST was essential to American prestige. And in order to underline the case for the SST, he appointed a committee. To his great surprise, I think, and consternation, the committee came out against the SST and decided it was completely unviable.
Apart from the sonic boom, the Boeing SST was encountering other problems. When he set the goal for the American SST, President Kennedy had decreed that it would fly faster than its European rival at Mach 3. But at that speed, an aircraft's skin becomes red hot. You have to make it of expensive materials that will not melt or crack at those temperatures.
To reach the speed that the 2707 was going to go at, you had to find new materials to deal with the buildup of heat. The most effective material would be titanium. And at that time, titanium was really, really complex to machine, very expensive to get a hold of. It was going to make the whole project uncommercial.
It's tough environment, and temperatures in Maine is a real big problem. Whether you can ever design a structure to meet all this and still have enough left over to make any money with is not too clear at this point.
The British had long since decided that these problems were too difficult and expensive to bother solving. Concorde would fly at less than 2,000 kilometers per hour, where the heating problems were much reduced. Concorde could therefore be built out of standard metal alloys to keep the manufacturing costs down.
You went much faster than Mach 2. We got too hot for aluminum. I don't know. Aluminum, I can't tell you exactly, but you wouldn't want to go too much beyond 2 to get to with aluminum. So you needed a better material. And titanium was quite capable. It was a good material, and we felt that it would be. So part of the program was learning how to manufacture.
As Boeing's engineers grappled with the problems, the 2707 program suffered delay after delay, while costs skyrocketed.
We spent several $1 million of our own company money in working titanium on the side of the outside of the contract on the SST, but maybe we were too ambitious. It might have worked at 2.5 Mach number, but I think that you go 3 and that's 400 degrees, and that's too hot.
On May the 18th, 1971, the United States Senate met to vote on a motion to end funding the SST project. President Nixon had worked hard to persuade the senators to keep on with the project, but without success. The Senate voted 58 to 37 to kill the Boeing 2707.
I think that Kennedy's decree that the SST should be bigger, better, and faster than the European rival did cause major problems for Boeing and for the whole project right throughout it, because they were always aiming for this kind of Kennedy standard of Mach 3 and all the problems that are associated with flying at Mach 3.
I think that was too hot. It just wasn't practical. I think we could go faster than the 2. I think 2.5 would have probably been okay from a temperature standpoint, but certainly any higher than that would have probably not been practical.
Europe looked like it had won the technological race. In 1973, only 18 months after the Boeing SST project was cancelled, Concorde made its first visit to the USA to attend the inauguration of the new Dallas-Fort Worth airport. During its 4-day stay in Texas, Concorde made supersonic demonstration flights over the Gulf of Mexico and proved to be the outstanding attraction in the flying displays, which formed part of the airport dedication ceremonies. But it would soon become clear that Concorde's victory was no victory at all. The problems that beset the Boeing 2707 and eventually killed it also affected Concorde, particularly the sonic boom. British Airways flew its first ever regular supersonic flight between London and Bahrain in the Persian Gulf on the 21st of January, 1976. Unfortunately, the route was mainly over land, forcing Concorde to fly at subsonic speeds on large portions of the flight. Next came the introduction of a service to Singapore. That on the 13th of December 1977, after only 3 return flights, service was suspended because of complaints from the Malaysian government about the supersonic boom over the Straits of Malacca on the west coast of Malaysia.
Ultimately, Concorde, though it made it into passenger service, it suffered the sonic boom problem that had dogged the early Boeing project. The Americans banned supersonic flight over the continental United States. Some people said that was in retaliation. Whether it was or wasn't is neither here nor there. It meant that Concorde could only fly supersonic over the Atlantic.
It couldn't meet any of the requirements that we couldn't meet. They don't meet the sonic boom, and they don't meet the takeoff noise, and I guess there are probably only half a dozen or so flying in each airline.
Concorde will never be profitable in the sense of making back the money that it cost to buy or to develop. As far as the airlines are concerned, well, Concorde makes money on an individual flight-by-flight basis because it can charge very high tickets to the kind of luxury passengers that are there.
The system exists now because it's unique and it's high cost and it's one of a kind. And if you want to make a splash, you go over on the Concorde. And okay, Betsy and I were on that one. We went over, take off from Washington about 4:30 in the we took off from Washington about 4:30 in the afternoon. And you're in a hotel room in London, 9 o'clock. It's great.
But there is one aspect of the Boeing 2707 story that has never been told. A development that was to usher in the age of airline travel for everyone. On December the 22nd, 1965, Boeing's chairman, William Allen, and Juan Tripp of Pan American Airways signed a letter of intent which committed Pan Am to purchasing 25 of a new cargo plane. Unlike the 2707 that was dominating Boeing's attention, the new plane was almost an afterthought. Boeing kept it simple. The design was just a scaled-up 707. They called it the Model 747. The world would call it the Jumbo Jet.
The 747 is an amazing story. And it started back right after the Vietnam War, where the government said, we need to move a lot of material and a lot of people around the world in a hurry.
The 747 was actually developed in tandem with the Boeing Supersonic project. And the aim was to put in the 747 what you couldn't get in the supersonic aircraft, which was freight. It was just meant to be a big cargo plane in the first place.
The Boeing company in 1965 decided to scale up the 707, I think as a freighter originally, but it was soon realized you could pack so many people into these aircraft and fly them at high subsonic speeds that it was very, very commercially viable, made great sense.
When the dream of supersonic passenger flight died, there was only one plane to step into the breach, the 747. The first 747 entered service with Pan Am in 1970 and started a true revolution in flying. Suddenly, the cost of long-distance air travel was within the budget of the ordinary family. The age of mass air transport was born.
I think the 747 will still be flying in 20 years. It's one of the major developments of this century in aerospace.
Curiously, there's one hangover from the old supersonic project that ended up in the 747, and that was the seating arrangement. When they transformed the 747, the jumbo jet, into a passenger plane, because it was wide-bodied, they could put in a couple of rows, you'd get a lot more seats. And that was the original dream that the supersonic transport had been born with.
But Boeing's interest in supersonic passenger flight did not end with the 2707. In Russia, NASA found a mothballed example of the Soviet SST, the Tu-144, nicknamed the Concorde.
The Russian SST actually flew just a few months before Concorde. And when people saw it, they said, gosh, that looks like Concorde. And that's because, of course, the Russians had stolen, line for line, page for page, the plans of the Concorde and built it themselves.
But the Concorde never entered international service. Soviet technical know-how was not up to the challenge of building a supersonic airliner, not even with the help of stolen plans. The plane proved difficult to fly and fundamentally unsafe. Its last outing was as a flying laboratory to try and solve the environmental problems that had plagued the old 2707. Engineers from NASA and Boeing envisioned a new supersonic jet that could fly 300 passengers at more than 2,400 kilometers per hour and cross the Pacific from Los Angeles to Tokyo in a mere 4.5 hours. But that was precisely the specification the old 2707 cancelled nearly 20 years earlier.
The main thing that's happened is you've gone to high bypass ratio engines, and the engine cycles changed, and the noise problem isn't as bad as it used to be with a pure jet.
20 years had brought more knowledge about building and flying complex supersonic machines. But the same old problems still stood in the way. A big supersonic craft designed to fly beyond the heat barrier would be incredibly costly to build, fly, and maintain. And there would still be pollution and noise.
There is no technology anywhere that I'm aware of that says that you can bypass, overpass, whatever, the supersonic barrier. It's there. The boom just has to be there. There's so much energy involved when you go through that barrier.
The dream of supersonic transport was an engineer's dream. It was a politician's dream. It was Kennedy's dream. The passengers wanted something different. They wanted cheap tickets. They wanted reliable service. They wanted comfort. And that will always be the future of the airline business.
Now, as a matter of fact, if somebody were to ask me today, will there ever be a supersonic airplane in the U.S. built by the U.S.? I would say first you got to define what you mean by supersonic. There may very well be a more advanced Mach 2 airplane, larger, more economical, and so forth than the Concorde. They may very well be. I don't know that. But we are still today not ready in materials to go to Mach 3. We just don't have the wherewithal to do it.
But the dream lives on. Even today, Boeing are still working on designs to push the frontiers of speed for passenger aircraft. The Lockheed SR-71 Blackbird flies at Mach 3. It is made of titanium, and metallurgy and materials technology are advancing all the time. Will the 21st century see the dream come true? This is the challenge and the true legacy of the Boeing 2707. If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.